anyhow, let's go through the. So if you want to build your own custom environment, it's essentially you have to think like some features for your environment, and these features are gonna capture the environment whatever you want to capture. Say if it's a wind turbine, it's gonna capture, say, the speed the turbine rotates, the amount of wind it goes through, amount of energy it generates, or the amount of thrust it generates, and the wind resistance and whatever you have. And if you say, oh, I'm gonna do like this chatbot, you have to say, okay, I have to log how is the conversation going on. They have for the image classification, what they do, they have an image and they have a template. And the template is like the sentences from the medical doctor. There's like a fixed template, and it's kind of like a Matlab. And the environment basically is like, oh, this is the image, and you have to generate the sequence of these template sentences. These are like fixed sentences. And then for each position, like for the first sentence, you have a set of tokens you can choose. And for the second position, you have a set of tokens you can choose, and so on and so on. And the reinforcement learning agent basically gets rewarded or punished based on the token it selects at each position. So you have basically a state, and then you allow whatever the agent to do an action on that state. And then you tell the agent, okay, this is your reward, and that's the next state. That's in a nutshell. And normally you set, okay, you have like, you set, okay, the super basically says you do the initialization from the super class. Like here it would be environment, German environment. So this just makes sure that whatever it's initialized, all the parameters, all the values, everything, it gets initialized as well. And sorry. Projector's not off. Today is like technical problems. Technical problems galore. And okay, so the super in it just says basically calls the constructor of the parent class. And the parent class here is gym environment. And this just makes sure that all the initialization that happens in a gym environment class happens here in your own custom class. So it does the kinds of like parameter initialization, streaming, whatever it does in the back in the curtain. It will do it for you, and it will make also kind of, this makes kind of sure that your class can be just used just as any other gym environment class. And then here we say, okay, our action space is whatever, or discrete action space, you can say, like, oh, I have 7 actions, you have 7, or whatever. It is continuous, you don't have this, you don't say space is discrete, you say like space is continuous, or whatever. Did it have to see it? Contain custom event close change n channels can contain custom. It's some other thing. Anyway. And then you have like some boxes, and this just basically says, okay, it's kind of pixel values, right? And it's like height and width and the number of colors, like 3 if you RGB. And then basically your environment space is like an image if you use space.box. But it doesn't need to be, like it can also be space.discrete or whatever. And then the space is also a discrete space, right?
So for instance, if you're doing for a trading environment, would we take the time slots as boxes? Would that be one part search? For hypothetically intraday trading,
Yeah.
so what would be the observation space that you would take?
It depends what you want to do, right?
Like say for instance, if you just take the half an hour, high, low, open, close.
Like daily or?
Yeah, just for say, just for an intraday position.
Yeah.
And say if you just cut it down to say about 5 hours of trading, and we say every half an hour we take or every.
Yeah.
So
Yeah.
how would that be the observation space?
Well, then your observation base would be exactly what we said. For 5 hours, you have the half hour ticks. Just as you said. And say, basically, you said, okay, step is kind of the step function. So if you say, okay, I do a certain step, it kind of calls the step function. and it has like some action parameter, which is kind of like can be a continuous or can be a discrete or whatever the action is. And what it does, it returns like kind of the info object, like the next observation, the reward, the episode, if it's episode true or false, like if the episode is over, it's true. If it's not over, false. And info is like some kind of dictionary object, which contains additional information. And basically, this is kind of just your next environment stuff, and it should be the same environment you have defined here. Like it should be the same dimension. And reward is kind of like a float. It goes like from minus infinite to plus infinite. And basically, this is like a true or false if it's the game is over. And this becomes some. You can use it for debugging or for diagnostics or what have you. And you say, okay, we have like some. This is kind of like a fixed thing. Like you say, okay, I take action, self-take action for action, and then say, okay, my environment, I take a step, so you get to the next environment. And then say your reward, you get your reward, and then, sorry, get state gets my, the basically step just does a step in the environment, and then you get your next status, like the internal status of your environment, you just update it. And then every environment gets state, it's kind of a function that just returns your current state giving an environment. And then, okay, if episode over, then say, okay, you have some kind of info like status, and you say you have some kind of enum or whatever, or say if it's the status equals this, then you say it's over, else it's not. And then you return it. And think of this more like an abstract class. So this is not a concrete implementation. And this is like kind of like, for each class, each of your custom implementation kind of extends this existing class, and you just have to write your own tag action function, your own get reward and get state function, essentially. This is and step function. And say reset is like kind of your own custom reset function. Like often we reset the environment, right? Each time we play a game at the beginning we say reset, just sets the game back at the beginning and returns you the first state. And then render is kind of like you make a visualization of the game. Like you saw the little video, what they do, they use the I forgot what the library called, p-image or something like something like this, and they use this to create the images from, like here you have a raw RGB array, you can convert the raw RGB array to an image, and what you do with the environment is each time you take a step you create the image, right? And then you just store all the images, and then you save the images as a video. That's it. Take actions, you do take an action, given an action. And then you say like a reward, and then you say, okay, if you have this, like foobar or whatever status, you give this reward. If you have like this reward, you get like whatever other reward, and else you just get no reward. And this is going to be, now we're going to go through the frozen lake example.
So when we set the reward, we set it for a specific action, or like how do you set get reward?
So you have like a get reward, and it just says self, right? And you have like self.status, right? You do an action, and then you update your own internal status, the status of the game. And each status has kind of like a reward associated with it. So here we say the card pull. It gives you 1 point. You have two status. The status is I'm running or I'm done. If you're running, I give you 1 point. If I'm done, I give you 0 points. And then status, if you're running, if you are done, then basically HFI pi info doesn't equal in-game. So you have like some HFI whatever pi, then you have an enum. Enum is like in-game, out-game, or whatever. So if your status is in-game, you're still playing, you get a 1 point, and if your status is out-game, you return I'm done and you get 0 rewards. Think of this more like a blueprint for it, not really like a real implementation. And say, okay, we have like some system importance, so good system, and then some string images, string IO just allows us to visualize the game. And we say, okay, we have some util, gem environment, and toy text, and we say these are our actions. And we say 0 is left, down is 1, right is 2, and up is 3. So we kind of define our action states here. And we say, okay, we have 2 games. One is a 4x4 map, and one is an 8x8 map. And we say S is safe, F is frozen lake, H is whole, and G is our goal. And the goal is like to go from here to the G. You go from S to the G while avoiding all the hoops. And we also have like something that allows you to generate random maps. They also need to make sure that you can win the map. See, so they check if it's valid. If not, you just do something else. You don't return it. And you say, okay, this is like a discrete environment, so they extend the discrete environment. It's a discrete game. And say, okay, winter is here. We were tossing around to say whatever flavor tags. We talked about this in the first session. And we say this is like the 4x4 maps, and it kind of explains what is what. And we have like 2, they say our metadata is like kind of like switches or sets or configs. And we say here our metadata is like modes, random modes. And we allow either human or ANSI. And ANSI is like kind of text, and human, I don't know what human does. So human prints out the nice map with the color code, and ANSI just returns you like some text. And basically, if you have no description and no map, it just generates a random map. And if the description is none, then you say, okay, just get my map, right? Get the map name. And there you just says, okay, you just number of rows, number of columns is like kind of the shape of the map. And this is kind of also your observation space. And the reward range is like basically 0 to 1. And NA is like my number of actions, is like fixed, it's always 4 actions, up, down, left, and right. And my number of spaces, basically all the spaces is like number of rows and number of columns. It can be at any position on the game map. And the ravel, it just kind of, I think flattens the array. So basically, it's like, instead of storing a 4x4, we just have one long array. And then we always unravel and unravel it, depending if we need it. And P is, this is for the if you have slippery is true. Somewhere you can have slippery. Okay. And if slippery is 2, P is just the probability of doing a random action at any position. You said we can just ignore it for now. And say, okay, to state, you have a row and a col, so number of row times number of col plus col, right? So basically I give you a E and a Y, and we have flattened the index, so it kind of translates the E and Y value to the position in the array. And this is kind of like, I have an index in the row, right? And my position on the maps, say I'm at position 3 and 2, like 3 from the left, 2 from the top, and I do a certain A is an action. I say I go left or I go down, I go right or go up. And then basically here it just says, okay, if I go left, how do I update the column? If I go down, how do the row? Then basically you kind of update the row of my column position, right? If I'm going down, basically my column stays the same and my row goes up by 1, right? If I go up, my row goes down by 1 and my column stays the same. And the same if you go left or right. Like if you go left or right, your row stays the same and your column changes. And this is like for the probability slippery. So and column. So it kind of does gets you the S for every row and column position. Which function is this? Oh, it's still doing the action, right? And then basically it gets the letter, right, for this description. And basically LE append. So it gives you the state. And the reward, no, this is something else. So if it's slippery, that's like a probability goes through, but you don't go with probability. So say the new row, new column is basically this ink, and this ink is kind of like the next position. Like I give a row, column, and an action, so it updates my state. Then say my new state is 2s, basically maps the e and the y of the matrix to the array, and then say okay, this is then my new state, it's like the position in the array, and then the new letter basically is the new letter is kind of like the position in the like the letter I stand on, like H or F or S or G. And done basically if I'm in a hole or I'm in a goal, then I'm done. Else I'm not done. So the letters are like stored in bytes, so I need to transform. And then reward is basically float new letter equals BG. So basically it's 1 if I'm at goal and 0 else. So I get 0 and 1. And then you just return, you just append this kind of, and then you return it. And render is kind of like just for the visualization, how to visualize it. And that's pretty much it for the frozen lake. And we can go through some wrappers, but are there any questions for the AI gym environment? So for the wrapper is the thing is like you give a wrapper, you give it an environment, and it just puts additional function on the environment. And there are like different things you want to do depending on your game. So there's a OpenAI have like common wrappers for the Atari wrappers for all the Atari games you play. And here is like kind of all the wrappers. And then this is like the other wrappers. Look at it. Like clip action just clips your action, right? You do an action, it's like a continuous action, right? And then you say, okay, my action I want to clip it between -1 and 1. So if I give an action of -2, actually you just give -1. And how do they work? Say this is the frame stack. So what they did for the deep Q learning, what they did is stacked 4 frames. So you didn't play every frame by frame. Rather, you get a stack of frames. You make a decision, you give back an action, and then you continuously do the action for this stack of frames. So you decide always the action for a stack of frames, not for each individual frame. And K is basically how many frames you want to stack. And basically frames is a DQ. We had the DQ in the previous session. It's like a array, a queued array. And basically if I add something in the array, it just overrides the last item and just shifts always going. And space, observation space are kind of my images, and then the observation space shape is kind of the shape. And reset just makes the queue empty. And you just frame observation. And observation. So basically, get observation. Now you return basically the stack, the list of frames, basic frames. And if you do a step, it just takes as action and appends the action to the frame, to the thing. And if you say you return the next state, you return kind of the stacked frames. You no longer return the single frame. So you do an action, you add the frame to your queue, and then when you return the next state, you always return the stack of frames. And this is again the clip reward. It just clips the reward between +1 and -1. Just clips it to +1, 0, and -1. So you have a reward, and NP sign returns you +1 if the value is positive, 0 if the value is 0, and -1 if the value is negative. You kind of map your reward into like, oh, you do the positive, you do the negative, you do neutral. Sorry, it's the reward, not the action. So it clips the reward. And what it does, basically you pass it an environment, right? And then it just initializes the wrapper, and basically what it does, the wrapper overrides the reward function. And then basically it just calls the reward after getting the reward, and then basically you assign the reward. See,
So
because you
how
have.
does this help us?
Hmm?
How does this thing help us? Like, where would we use something like this?
I think if you have a game, and the game has like some continuous
Okay.
plus and minus, but for the training you just do plus and minus and 0. You don't care about the continuous. And basically this max and skip environment and the frame stacking, they just go hand in hand. So this basically skips end frames, and you just do the same action for the end frames. So what it does, it updates the step function, overrides the step function, and then I say I do an action, and then for range n, it just skips the frame, so it just does nothing, and it just always passes the action. It always passes the same action for each frame you skip. And basically if you're in the last or in the second to last frame you skip, you can return, like you have observation buffer, you take those 2 observations, right? And the total reward is just the sum over all the rewards. Say you skip 5 frames, you do the same action for the 5 frames, the reward for the next step would be the total reward of those 5 frames you skipped.
So this would be like Mario and like not just holding forward or not doing anything for 5 frames?
So what it does is basically if your agent decides I go forward in Super Mario, it does, instead of doing it like for 1 frame, your Mario is going to do it for 5 frames.
But it's always 5?
No, it can be 3, 2, 1. I think they do 4 or 5 in the deep Q learning paper.
I mean, dynamically within a given run, will that number change or it'll always hit 4?
It's always not dynamically in the game.
Because that's what the preprocess.
Yeah. And basically the observation, the max frame, it just returns the maximum of those 2 observations. And that's it. So these kind of wrappers allow you to put like functionality on top. So these things they do, the frame stacking, frame skipping, I think they got better results and also faster results because you don't have to train and evaluate for every frame. The information between 2 frames, they barely change, especially if your input is an image, right? Like how can your neural network, like, it makes it much harder or easier to learn if you skip a few frames because more in the game can change.
Because one of the things that I was reading, they look at the differential between the pixels.
Some do it, but I don't know if they do it for the deep Q learning.